This video goes with factors that affect solubility. This is in the above and beyond section, so of course it is optional. But if you are planning to go to college and think you may see this stuff again sometime, then it's a real good idea to go through this one. All right, factors that affect solubility. Reflect. Imagine you are making lemonade by stirring lemonade mix into a glass of water. 1 spoonful of mix would likely dissolve easily in the water, producing a solution. A solution is a mixture of 2 or more substances spread evenly together. What would happen if you added another spoonful of mix to the solution? Depending on how much water is in the glass, the additional mix may take longer to dissolve. If you add another spoonful or 2, you need to reach the point where the lemonade mix no longer dissolves in the water. The lemonade mix that does not dissolve settles to the bottom of the glass. Why is there a limit to how much lemonade mix dissolves in water? Factors that affect solubility. Water is one of the most abundant liquids on Earth, and it also is one of the best solvents. A solvent is a substance in which another substance dissolves. Water dissolves many types of substances. Solutions in water is used as a solvent known as aqueous solutions. Why is water such an effective solvent? An important reason is that water molecules are polar. In other words, they have opposite partial charges. A water molecule consists of 2 hydrogen atoms, H, each shares its own electrons with the central atom, O. The shared electrons are attracted more to the oxygen atom, so it acquires a partial negative charge. Meanwhile, the hydrogen atoms acquire partial positive charges. Okay, here's your water molecule. You can see this little symbol means partial, so this is partial positive right here, and then partial negative over here. We talked about this before, positive Mickey ears, negative Mickey chin. A water molecule is polar. The oxygen atom, red, has a partial negative charge, and each hydrogen atom, white, has a partial positive charge. Partial negative, negative, positive. Ionic compound. A compound formed between a negatively charged ion and a positively charged ion. What does this have to do with solubility? When other polar molecules or ionic compounds are mixed with water, their positively charged components are attracted to the oxygen atoms in the water molecules, and their negatively charged components are attracted to hydrogen atoms in water molecules. Ions are particles with electrical charges. The chemical bonds joining some compounds are strong enough to withstand the attractive forces from water molecules. Other compounds, however, are broken apart. This is what happens when a substance dissolves. In contrast, nonpolar substances such as vegetable oil do not dissolve water. Instead, the denser substance sinks beneath the less dense substance. Page 2. Look out. The temperature of a solution also affects the solubility of a solute. Typically, at higher temperatures, the solubility of a solid and liquid solutes increase. You can dissolve more lemonade mix in hot water than in cold water. In contrast, at higher temperatures, gases are less soluble in liquids. If you were to leave a can of soda in a car on a very warm day, it might explode. The soda is a mixture of gas, carbon dioxide, and liquid, water. At warmer temperatures, the gas particles move more quickly, so it is easier for them to escape from solution. As they collide with the greater force against the walls of the can, pressure builds inside the can. Eventually, the pressure may cause the can to explode. Changes in pressure do not drastically affect the solubilities of solids and liquids. However, pressure changes can have an enormous effect on the solubilities of gases in liquids. At high pressures, gases are more soluble than at low pressures. This is a serious concern for scuba divers. Air is a mixture of gases, primarily nitrogen and oxygen. As we breathe air, these gases are dissolved in our blood. Deep underwater, the pressure is much greater than at the surface, so a scuba diver's blood contains more dissolved nitrogen and oxygen. The body cannot use the extra nitrogen, so as the diver begins to ascend, the extra gas is forced out of the blood, forming bubbles that go into the bloodstream, into tissues and muscles. Divers who ascend too quickly may suffer from decompression sickness, or the bends, pain or weakness throughout one's body, and, in some cases, shortness of breath. To avoid getting the bends, scuba divers should surface slowly. This allows nitrogen gas dissolved in their blood to come out of the solution in smaller amounts over a longer period of time. Reflect. One definition for an acid is a substance that lowers the pH of a solution and the acid's concentration is increased. A base, on the other hand, is a substance that increases the pH of a solution if the base's concentration is increased. But different acids have different effects on pH. Some acids, such as hydrochloric acid, are strong and have a large effect on pH. Others, such as acetic acid, are weak and change pH only a little. This has to do with the substance's percent dissociation. Strong acids react completely, becoming completely dissociated. When an acid dissociates, it releases hydrogen ions into solution. This, in turn, lowers the pH. Because strong acids completely dissociate, they release many more hydrogen ions than a weak acid. Weak acids do not completely dissociate. Some weak acids have less than 0.1% dissociation. Thus, they affect pH much less than strong acids. Percent dissociation, a measurement of how much of a dissolved compound breaks into its constituent ions in solution. The same concept holds true for strong and weak bases. The only real change is bases release hydroxide, which decrease the amount of hydrogen in solution. Weak bases still have less than 100% dissociation, while strong bases have 100% dissociation. Page 3. What do you think? The following graph shows the effect of temperature on a solute dissolving in a solvent. The x-axis shows the temperature of the solvent in degrees Celsius. The y shows the mass of the solute in grams that dissolves at each temperature. What can you conclude about the relationship between temperature and solubility for these substances? Okay, so we've got the mass over here, the temperature over here, and you can see it's getting bigger, 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 bigger as it gets hotter. So higher, it can hold more at a higher temperature. Identifying electrolytes and non-electrolytes. A common way to classify aqueous solutions is to determine whether they are able to conduct an electric current. An electrolytic solution conducts electricity. These solutions contain electrolytes, substances that separate into ions when dissolved in a solvent. The ions are electric charges which can move within the solution, allowing it to conduct electricity. A non-electrolyte solution does not contain electrolytes and so does not conduct electricity. The diagram at the right shows a conductivity meter. Do you think the meter is connected to an electrolytic or a non-electrolytic solution? If an electrolytic solution is connected to the conductivity meter, electric current will flow to the bulb and produce light. If it's a non-electrolytic solution is connected to the meter, the light bulb will not turn on. So I'm guessing this is not turned on, so this would be non-electrolytic. If it showed maybe some little mark saying it's on, then that would be electrolytic, who would contain electrolytes. Sodium chloride, NaCl, is a strong electrolyte. When sodium chloride dissolves in water, the sodium ions and chlorine ions separate from each other. The ions disperse evenly throughout the water, which becomes an electrolyte solution. Here is the chemical equation to describe sodium chloride dissolving in water. Sodium chloride, which is a solid, in water makes sodium ions and chlorine ions. In contrast, substances such as ethanol, C2H5OH, and normal table sugar or sucrose are non-electrolytes. A granule of sugar large enough to use to see consists of many individual sugar molecules joined together. When sucrose dissolves in water, the connection between the different sugar molecules are what break apart, not the sugar molecules themselves. The resulting solution contains evenly dispersed water and sugar molecules. Because ions are not produced, the solution does not conduct electricity. Here is the chemical equation to describe sucrose dissolving. Sucrose mixed in water still is sucrose. So look at the difference. If it's an electrolyte, it breaks apart into two different ions. If it's a non-electrolyte, it's the same molecule before and after. The molecule does not break up. Okay, page 4. Look out. Do not confuse molecules that are polar and compounds that are electrolytes. Polar molecules have partial charges. One end is partially positive and one end partially negative, but they are not composed of ions, which have full positive or negative charges. Like electrolytes, polar molecules dissolve in water. Unlike electrolytes, however, polar molecules do not break apart into ions when they dissolve, so they do not produce electrolytic solutions. For example, table sugar is a polar molecule that dissolves in water and is a non-electrolyte. In contrast, table salt is an ionic compound that dissolves in water and is an electrolyte. Types of solutions. Recall the glass of lemonade at the beginning of this companion. Initially, a small amount of lemonade mix was added to the water. The resulting solution was unsaturated because additional solute, the mix, could be dissolved in the solvent, the water. More lemonade mix was added until eventually no more mix would dissolve. At this point, the solution was saturated. Any mix added after this point settled on the bottom of the glass. It is possible to dissolve more solute in a saturated solution by increasing the solution's temperature or the pressure acting on it. Such a solution becomes supersaturated. When a supersaturated solution is brought to normal pressure or temperature conditions, the additional solute precipitates from the solution. Precipitates means becomes a solid. Adding more solute or distributing the solution, for example, by tapping on the container, can also trigger this precipitation. Many supersaturated solutions form crystals. In an unsaturated solution, A, more solute will dissolve in the solvent. In a saturated solution, B, no more solute will dissolve in the solvent. In a supersaturated solution, C, additional solute has precipitated out of the solution to form crystals. I don't really like their final definition here. Supersaturated means it contains more solute than it can. It means you've heated it up and allowed it to cool, so there's more dissolved in there than should be able to dissolve. Factors that affect solubility rates. The speed at which a solute dissolves is in a solvent, or the rate of dissolution, depends on three factors: the temperature of the solution, the agitation or mixing of the solution, and the surface area of the solute. If any of these three factors change, the rate of dissolution changes. Surface area. When the surface area of a solute increases, the dissolution rate also increases. Suppose you had a spoonful of sugar granules and the same amount of sugar pressed into a cube. The spoonful of sugar has a greater total surface area than the cube because each granule in the spoonful contracts the solvent separately. So the spoonful of sugar will dissolve at a faster rate than the sugar cube. A spoonful of sugar granules, left, has a greater surface area than the sugar cubes, right, and a faster dissolution rate. Page 5. Look out. Solution temperature. Heating a solution causes the particles in the solution to move more quickly. As a result, the solvent and solute particles collide more frequently and with greater force. Therefore, when the temperature of a solution increases, the rate of dissolution increases. Lemonade mix dissolves more quickly in hot water than in cold water. Agitation. Agitating a solution increases dissolution rate. If you stir lemonade mix into the water, the mix dissolves more quickly. A washing machine spins as it cleans your clothes to help detergent dissolve more quickly in the water. Getting technical. Lithium-ion batteries. Many modern electronic devices, including computers, cell phones, and portable music players, are powered by rechargeable lithium-ion batteries. Inside these batteries, the movement of lithium ions and electrons generates electric current. A battery is made of three parts: a positive electrode, a negative electrode, and an electrolytic solution. The positive electrode of a lithium-ion battery contains lithium cobalt oxide. The negative electron is made of carbon. The electrolytic solution contains various lithium salts as listed here. Because they are electrolytes, these lithium salts dissociate into positively charged lithium ions and negatively charged polyatomic ions as the battery charges. The lithium ions move to the negative electrode. As the battery is used, the lithium ions move back to the positive electrode. The result is an electric current able to power electronic devices. Inside a lithium-ion battery, lithium ions move between the electrodes, creating an electric current. Okay, and finally page 6. What do you know? The following terms are associated with electrolytes and non-electrolytes. Write each term in the correct place on the Venn diagram on the next page. Place terms associated with both electrolytes and non-electrolytes in the middle. Alright, so let's look at the first one. MgCl2 dissolves in water. Magnesium is a metal. So because magnesium is a metal, MgCl2 is going to go under electrolytes, because anything that starts with a metal that makes an ionic compound will break apart, and so that's going to be right here in the middle. Okay, you know what? I'm just going to number these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I'm going to put the numbers down instead of writing all of those out. Alright, so there's one right there. Alright, the second one will dissolve in water. Well, sugar and salt both dissolve in water, so regardless, electrolytes and non-electrolytes will dissolve in water. So we'll put 2 right there. Conductor of electricity. That's going to be only the electrolytes. If it dissociates into ions, an ionic bond starts with a metal, then it'll be under electrolytes. Okay, this one starts with hydrogen. That's a non-metal, so this is going to be under non-electrolytes. Does not dissociate in solution. This will be under non-electrolytes because it doesn't break apart or dissociate. Then it doesn't conduct electricity. It doesn't break apart into ions. So this is a non-electrolytes. Can be polar substances. This is going to be both polar and non-polar, doesn't matter, with electrolyte and non-electrolyte. They don't have anything to do with each other, two separate concepts. Dissociates into ions. That is electrolyte. That's what causes it to conduct electricity. Lights a bulb when connected to a conductivity meter. That's electrolytes. Not an electrical conductor. That's your non-electrolytes. Does not light a bulb connected to a conductivity meter. No lighting of the bulb. The end.